All right, let's dive into one of the most just mind-bending experiments in all of science. Seriously, we're talking about the double slit experiment. And it all kicks off with a question that sounds like it's straight out of science fiction.
So here it is. Can something, anything, be in two places at the very same time? I mean, everything you and I know about the world screams no way, right? But what if I told you that on the tiniest, most fundamental level, the universe's answer is, well, it's a lot weirder than you might think.
Okay, so how do we even begin to answer that question? Well, we're going to look at what seems like a really, really simple experiment. Imagine this. You've got three parts. First, you've got a little machine, kind of like a tiny pea shooter, that fires particles of light. We call them photons. But it fires them just one at a time. Got it? Okay. Next, in front of that, you put up a wall, a solid barrier, but it's got two skinny little slits in it, side by side. And finally, behind that wall, you have a screen that acts like photographic film. It'll show us exactly where each photon hits. Super simple, right? What could possibly go wrong? So if you're shooting tiny little baseballs through those two slits, what would you expect to see on the screen behind them? You'd expect two lines of hits, right? One line behind each slit. That's just common sense. But that is not what happens with photons. Instead, you get this, a whole bunch of lines. It's called an interference pattern. And it's where things start to get really, really weird.
So what in the world is going on? Why this strange pattern? Well, this pattern is exactly what you'd see if you sent waves through the slits, not particles. Think about dropping two pebbles in a pond. The ripples spread out, they pass through each other, and where the peaks meet, they get bigger, and where a peak meets a trough, they cancel out. That's what creates those stripes. But wait a minute. We're firing photons one by one. They're supposed to be particles, right?
And this is the part that should really blow your mind. Remember, we're firing these photons one at a time. There's only one photon in the whole setup at any given moment. So there's nothing for it to interfere with. And yet over time, as they land one by one, they still build up that wave pattern. The only way that makes sense is if each single particle is somehow going through both slits at once and interfering with itself. Yeah, I know.
This bonkers result leads us to one of the absolute pillars of quantum mechanics, something called wave-particle duality. It basically says that tiny things like photons aren't either a particle or a wave. They're kinda both. It's like they travel as a ghostly wave of all possibilities, but the moment they hit the screen, bam, they land as a single solid particle. It's a completely different rulebook from the world we live in every day. Okay, so scientists, being scientists, couldn't just leave this alone. They're thinking, no way, a particle can't be in two places at once. We're gonna watch it. We're gonna find out which slit it really goes through. And when they decided to look, well, the universe had another curveball ready to throw. So here's the billion-dollar question. What happens if we put a tiny little detector right at the slits? Something that'll tell us, hey, this photon went through the left slit, or this one went through the right. It seems like a perfectly reasonable thing to do, right? But the answer to this simple question changes everything. The second you turn on that detector, the second you try to watch which slit the photon goes through, the interference pattern just vanishes. It's gone, poof. And what do you get instead? You get two solid lines, exactly what you'd expect if you were shooting tiny baseballs. It's as if the universe knows it's being watched, and the very act of looking forces the photon to stop acting like a wave and start behaving like a good old-fashioned particle. This is a phenomenon with a very cool name, wave function collapse. Before we look, the particle is in what's called a superposition. It's not left, it's not right, it's a cloud of pure potential, a wave of all the places it could be. But the moment we measure it, the moment we observe it, that wave of possibilities just collapses into one single definite spot. It seems that reality, on this level, literally waits for us to look before it makes up its mind. Now, as you can imagine, this result drove physicists crazy, and it led to one of the greatest intellectual showdowns of all time. We're talking about a real clash of the titans, Albert Einstein versus Niels Bohr. And this wasn't just some academic squabble. They were fighting over the very definition of reality itself. In one corner, you had Albert Einstein. He absolutely hated this idea. He just could not accept a universe that was based on chance and observation. His famous line was, "God does not play dice." For him, there had to be an objective reality out there. The moon is still there even when you're not looking at it, right? He believed there was some hidden rulebook we just hadn't found yet. And in the other corner was Niels Bohr. He basically looked at Einstein and said, "Get used to it."
Bohr's view was that at the quantum level, things aren't real in a way we understand until we measure them. The act of looking doesn't just discover reality, it helps create it. And for the better part of a century, these two ideas were at a total stalemate. So for 100 years, this epic debate just hung in the air. Who was right? But then, very recently, scientists at MIT designed a truly brilliant version of this experiment, one so clever it could finally deliver a verdict. So what did the team at MIT find? Well, they performed this incredibly precise test, and they proved, beyond a shadow of a doubt, that any attempt to find out which path the particle took, no matter how subtle or clever, instantly kills the wave pattern. It cemented this fundamental rule of the universe. You can have the wave, or you can have the particle, but you can never, ever have both at once. And the winner of the century-long debate? It was Niels Bohr. Hands down. And to put it in perspective, Nobel Prize winner Wolfgang Ketterle, who was involved in the research, said that this was basically a thought experiment that Einstein and Bohr could only have dreamed about 100 years ago. They were finally able to build the very thing these two giants could only argue about. So where does this leave us? What's the big takeaway from all this weirdness? It means we have to let go of our old ideas. The universe, down at its very core, just doesn't follow the same rules as our everyday world. You see, the most important lesson here is that our common sense, our intuition, it's completely useless at the quantum level. It's built for a world of throwing rocks and catching balls, but the fundamental reality is a place of probabilities and possibilities, where the act of looking isn't a passive thing. We're not just spectators, we're participants. And that brings us to the final and maybe the biggest question of all. If the very building blocks of our world change their behavior just because we look at them, what does it even mean for something to be real? A pretty heavy thought to end on, right? Thanks for diving down this rabbit hole with me.